Okay, welcome everyone to the third talk in our quantum summer series hosted by the Harvard-Radcliffe Society of Physics students. My name is Andrew Initsky. I'm an undergraduate studying physics and math at Harvard, and I'm one of the organizers of our Chilloquium speaker series. I'm here today with my co-moderator, Sambura, and we're very honored to have Professor Immanuel Bloch from the Max Planck Institute for Quantum Optics speak with us today. As always, if you have questions at any time, you can raise your hand in the Zoom participant sidebar and we'll call on you, or you can privately send a message to me and I'll ask for you. We encourage you to raise your hands to ask questions yourself in person in order to make this feel as conversational as we can. So we'll generally be prioritizing questions asked in person over privately messaged questions. In the spirit of keeping this a more relaxed and personal conversation, we also request that everyone be muted unless they're speaking and also have their video on if you're willing and able. Lastly, for those of us who are joining us for the first time today, and if this talk is the first, if this is the first time you've received one of our emails, please sign up to our Chilloquium mailing list on the link I just posted in the chat. This is just to make sure we don't miss sending you the invitation in case you're not already in our mailing list, such as on the Harvard SPS list. We send out one weekly Chilloquium email and a reminder on the day of the event. So if you want to stay up to date on what talks are coming up, fill out that quick 15-second form. And we usually send them out on Wednesday or Thursday. So if you are getting our emails a little bit delayed, like on Friday or whatnot, then you should probably sign up to onto that mailing list so you can get the emails directly from myself. All right, so with that, let's get started. Professor Immanuel Bloch is Scientific Director at the Max Planck Institute of Quantum Optics and Professor for Experimental Physics at the Ludwig Maximilian University in Munich. His research focus lies on the investigation of quantum many-body systems, quantum simulations, quantum information processing, and quantum optics. Professor Bloch, thank you so much for joining us today. It's really an honor to have you speak with us.
Yeah, thanks, Andrew. Thanks, everybody. So let me get started with my presentation. All right, do you see that? Did that come up? And it's changing slides also? Yep. Change? Okay, great. Okay, so it's a real pleasure to be here with you and be here to discuss with you. And as Andrew said, I would really appreciate if you just jump in if there are any questions, comments, make it as conversational as possible. That's going to be much more fun for me as well. And yeah, let's hope it's an interesting hour or so for you, and hoping to answer any of your questions and give you maybe some advice of how my scientific life went, career, and maybe what you're interested to learn about. So yeah, let me get started and give you a little bit of an outline of what I want to talk about. So obviously, we want to talk about our scientific, what we're doing scientifically, what we're interested in. So that will be mostly the second part, but as Andrew said, you also would like to learn a little bit more about my scientific career, how everything went for me, how you maybe, these things, you can get some advice for your own scientific career. So I'll start out with that actually, and then we'll get to the scientific part later on. Okay, so actually, I was born in Germany in a actually very small village with 200 people, more cows than people, in a town close called Schlüchtern, which is in the state of Hessen. It's actually close to the city of Frankfurt that you know probably from the airport. It's the biggest German airport and one of the bigger German cities. And that's where I basically grew up. I did my high school there, and afterwards, and I started out actually learning a bit, my interest. My father was a chemist, so obviously I was already maybe inclined towards natural sciences. And I started working there in a local company, doing some soldering and electronics, and I got interested, and I thought, what could I do? But and then I thought really physics was a good idea to study physics, because you could combine kind of all these interesting things of working with electronics, but then again combining natural sciences, maths. That's pretty much all I liked, and I really wanted to do something else than my father. That was maybe also something that I didn't want to follow his footsteps directly. I didn't want to become a chemist. That just sounded also too much cooking to me, then not really too a little bit too empirical for my taste. So then I went actually to the University of Bonn, which is here, the former capital of Western Germany, to study there. That's kind of a mid-sized town in Germany. Actually, it was really great as a student because it was, it's a big university, it's almost 40,000 students. But it was a mid-sized town, and it didn't feel, me coming from a small village, it didn't feel like, getting swallowed by Berlin or some of these huge cities we also have. And so I did my studies in Bonn, and then at that time we didn't have masters yet, so we had this diploma system. You might have heard about that before. Now we also have the bachelor and master system, like in the US. And so basically I did my diploma there. And then I really wasn't so sure what to do. And then I went for a research internship to Stanford University to work with Mark Kasovich there for a year. And that was great because I made a lot of contact with a lot of people there. I made good friends there that still are friends today to me. So that was a very important stay. And afterwards, I basically thought, should I stay in the US or should I go back to Germany to do my PhD? And so I was really thinking hard of staying in Stanford or going to Yale with Mark Kasovich at the time. He was moving his group to Yale. And one thing that didn't work out so well for me was that the German system wasn't that compatible with the US system. So with the German diploma, you were already like at the master stage in the studies in the US. And in the US, nobody wanted me to, they always wanted to have me do the 6-year PhD. And I really didn't want to do that because I already had the first 2 years done in Germany. So in the end, I ended up going back to Germany. Went to Munich to study with Ted Hensch, to do my PhD with Ted Hensch. So let's go through my CV a little bit. So you see this here written down from my CV. So I did my studies at University of Bonn, finished with my diploma, then went to Stanford for a year, which I really was really great. And I have to say it was a year that really didn't fit in so well in the sense of optimizing your time. This is really additional time I spent. So it really went on top of everything, but it was extremely valuable. So one advice I can already really give to you, don't try to just over-optimize your CV in a sense. When you think there's something good that you could do in a year or so, but it doesn't really optimally fit maybe into a compressed CV where everything is streamlined, I really highly encourage you to do that. For me, that was really great and it worked out fantastically. And I really, as I said, I've made great friends and contacts that really long-term have been extremely important to me. Yeah, and then I went to Munich to do my thesis, PhD thesis with Ted Hensch, who you know quite well probably in AMO, atomic molecular physics. He got the Nobel Prize for the frequency comb. It was not something I was involved in, and I was involved in the ultra cold atom research, but I was there pretty much in his group when all these developments were coming up in another branch of the group. So it was pretty exciting time to be there and also witness this time when the frequency comb was basically developed. Yeah, so I did my PhD in, you see, quite short time, 2.5 years actually. But remember, that sounds extremely short for a US person, but remember, you have to add my 2 years of master part to that. So it was really like comparably a 4.5-year PhD, but that was still short. I mean, that's also at German standards, that was shorter than usual. Yeah, and then I went on actually to continue in Ted's group. And that was, I think, where I made my biggest scientific discovery. So in my PhD, we worked on these already on ultra cold atoms, on atom lasers, and trying to investigate the coherence properties of Bose-Einstein condensates. So really like in a laser where you measure coherence of a laser, we really devise schemes how to measure coherence properties of ultra cold quantum gases when they're above the phase transition, when they're a thermal gas, or when you cool them below the phase transition and they become a Bose-Einstein condensate. And that was really at that time, that was a very interesting topic, very big topic. It got me in my PhD to the cover page of Nature. So that was obviously something I was very proud of. That was great. And that was an interesting time. So that was basically what my PhD was about. And then I decided, and that was unusual a bit because everybody tells you after your PhD, you should do your postdoc somewhere else. You should go and leave the group, change teams and go somewhere else. So again, I did something that was not so usual. I just decided to stay with Ted because he gave me a unique opportunity to build my own team there, become a team leader, to lead a small group of scientists there. So that's the spirit of how he was running in his group at that time and how basically I run my group today. And he gave me the chance to basically do what I wanted to do. Okay, so he didn't tell me what you should do. He didn't really tell me you should do this type of research or that type of research. He really gave me the freedom to do what I wanted to do. And at that time, there were these interesting proposals around of how to trap ultra cold atoms in optical lattices. And there was this proposal from Peter Zoller's group and Ignacio Sirac on how to do this superfluid to mod insulator transition. And that was pretty hot topic at the time, because it was really for the first time, showing how you could go from these weakly interacting condensates, which are described by this Gross-Pedayevsky equation, and do something that was really relevant for modern condensed matter physics, where people even like in Harvard, Subir Sachdev gets excited about. Okay, so that was really a big step, yeah, and really, so that got me motivated. I wanted to work on this with my team, and actually, I got really great graduate students to work on that team. So Markus Greiner was a grad student of mine in my team. He was the first student I hired, so that was a good choice, as you can probably tell, in Harvard. So Markus, myself, and Tilman Esslinger was also involved at that time, and Olaf Mandl, a master student, diploma student at the time. We had a small team of three or four people, and we did this experiment. And yeah, and that was my biggest breakthrough, I would say, in terms of scientific, impact. This quantum phase transition from superfluid to mod insulator. That was a really, I think, is still today my most cited paper, about over 7,000 citations right now. And I think it really was a game changer to the field, because it really, as I said, changed going from these weakly interacting condensates with the Gross-Pedayevsky equation, where some condensed matter physicists were saying, well, this is, we know this from the 60s, this is nothing new. I think it's unfair to say that, but that's what a lot of them said. And now suddenly we were doing things that were really at the heart of what they were interested in also. Okay, so that really changed the game in a sense of what you could do with these ultra cold quantum gases to really show that there's absolutely exciting physics, very exciting modern physics that you can look at.
Do you mind explaining the cover to
sure.
Undergraduates, maybe at a slightly simpler level? But yeah.
Sure. So in this, we're talking about really two phases of matter that can occur. So in this Bose-Einstein condensate, you can think of this gas cloud as really just a coherent wave, a coherent matter wave. Like coherent light coming out of a laser. Bose-Einstein condensate is like a coherent matter wave. And this coherent matter wave then also, gives rise to diffraction effects, interference effects. And when you diffract these matter waves of gratings, in this case, light gratings, so the roles of matter and light are reversed here. Usually, in undergrad courses, you diffract light from material gratings, but you can also diffract matter waves from light gratings. This is light optical potentials. I'll talk about those in a second. And this is actually what you see. So when you're there in a BEC, in a Bose-Einstein condensate state, you see this nice diffraction peaks. All right, this is the interference pattern here from this Bose-Einstein condensate diffracted of a light grating. And you see a pattern like you would see when you look at an interference pattern of light diffracted from a material grating, a square grating. And now you could, when you would make these interactions between these atoms very, very strong, you would suddenly find that now they lose this coherence and they enter this new phase of matter, which we call this mod insulating state. I'll tell you in a second a little bit more what is so interesting in this state and what microscopic properties it has. But you can immediately see this is not, this is not a coherent matter wave, because it doesn't show any coherence anymore. You don't see the diffraction pattern. But when you made the interactions weaker again, you could see that you can reversibly go back to the Bose-Einstein condensate. So as a function, basically, these three pictures show how, as you tune interaction strength, you can go from a weakly interacting state, these coherent matter waves, to a strongly interacting state of a mod insulator, and back to a weakly interacting Bose-Einstein condensate when you turn the interactions back down again. So you really have a reversible phase transition that occurs. And since this happens, even at zero temperature, we call this a quantum phase transition, because it's only driven by the quantum fluctuations in the quantum manybody system. And that's what, people like Subir wrote whole books about this quantum phase transitions. It's a really exciting topic in modern condensed matter physics. Huh? Yeah, so that's the superfluid to mod transition. That was I would say, scientific breakthrough. And that got me a lot of attention, I have to say. And I was very young at that age. I was like around 30 at that time, 31. And then it immediately resulted in, offers from Stanford, from Yale, and also from Mainz University to nice professor positions, which I then decided to go to stay in Germany, to go to Mainz University and become full professor there in 2003. And there I basically stayed for the next 7 years, continued working on these optical atoms and optical lattices, quantum simulations and optical lattices. And I'll tell you a little bit more what we did during that time. And that worked out quite well also this time in Mainz. And that was my next scientific step. Then again, I had a couple of offers for positions both in the US and in Germany. And then the Max Planck Society decided to make me an offer to come back to Munich to join the institute here in Munich, the Max Planck Institute for Quantum Optics. And that was a great opportunity for me to return to Munich and to my roots on the one hand, a place that I knew very well, but also to a place, I don't know if those of you who know the Max Planck Institutes, they are very prime institutions for fundamental research in Germany, covering thematically very different fields. For example, from biology, CRISPR-Cas, Emmanuel Charpentier is working in such institutes. Many other people in very different fundamental fields of sciences, natural sciences, but also humanities are working in these different institutes scattered throughout Germany. And we have one on quantum optics, headed by 5 directors in Garching, close to Munich. And I'm also at the same time a professor at the Ludwig Maximilians University in Munich. So to understand the system, these institutes, these Max Planck institutes, they are basically fundamental research institutes, but they are not universities. So they don't give, let's say, PhD degrees. And we are always associated to a university. So we can also teach at universities. And so I'm full professor at the university and teach there, lecture there, give courses there. Get your PhD degree through this university affiliation. Yeah, and more as the older I'm getting, the more I'm also getting involved in administration. That's the maybe downside of your scientific life. As you get older, you let the young people do the fun stuff, and the older guys have to do the more administrative work, also that the system keeps running. And so I'm now, been twice now, and again now I'm managing director of our institute. And I'm also vice dean of the faculty of physics at LMU Munich, and so I'm involved actually in a lot of administrative work as well. But I really enjoy science, and I really want to focus my work on science. So that's really why I'm doing all of this. But as you get older, this is kind of a little bit inevitable, and you want to give the freedom to the younger people so they can start their career and have the freedom not to do this administrative work. So that's my career up to now. And so I'm, not 47 anymore. I'm 48, actually turning 49 this November. And so yeah, it's been quite a ride and fun. I have to say, if you ask me, was there anything special you did? I think what really helped me, I always really worked on problems I really found challenging, I found exciting, interesting. I also tried to always pick directions that are not at that time the mainstream, that are not followed by most other researchers, but where I see a lot of potential for future research. And the third thing, and I think that's also just inevitable, is just also you need some luck also is in the game. That's very clear. It could have happened that these things don't work out so well, and so there's always an element of luck involved as well.
Yeah, Professor, if I may interrupt and ask a question, what was your sort of reason for choosing a professorship in Europe and Germany in particular, as opposed to one of these universities in the US?
Yeah, I think it was very close. I was always torn between, I really liked the US a lot, and I liked being there. In the end, I think it was personal choice of lifestyle, Europe versus US. And I think the offer then from Max Planck, this was really a unique offer for me. There's just, the core funding we get at the Institute gives me so much freedom to focus on science and not having to, spend so much time, at least on grant applications, that was very attractive for me, that to have an offer where in the long term, I would have the freedom to work on what I want to work on without justifying this to anybody, basically, So that's pretty unique. Of course, there are checks and balances in the system as well. So I can't just, go off and do whatever I want. So people will look and see if what we're doing is scientifically good, and we have our scientific advisory board. But yeah, that was basically, I think, the point where I said, yeah, that's a unique opportunity, I think, to work under such conditions. And yeah, I think in the end it comes down to personal lifestyle. I think if you have been to Europe or the US, there's just slightly different feel there, and so that played a very important role to me in my final decisions also. Yeah. Any more questions on the CV part? Okay.
I think I received one question in the chat. So the question is, I was wondering if you could tell us about how you interact with your team members. Is it different from, I think, groups in the US?
I don't think it's so different. So what we do, okay, so let me explain. We have typically on the experiments, we have teams of about 5 people. So typically we have a team leader, which is kind of a very experienced postdoc, or more, it's not normal postdoc, somebody who already did his postdoc, but now is at the stage after the postdoc. So that's what we call the team leader. That's a senior team leader leading the team. And that person is there for, let's say, the day-to-day interaction with the team, any questions the team has. And I'm always available for questions. We have weekly team meetings, so where we come together. Now, of course, everything in Zoom. Usually we do this in presence. And with every team, we have weekly team meetings where all of us come together, and there's a presentation from everybody in the team, what they're working on, what the current problems are, what the status of their research is, and then we decide together what the next way forward is. I have to say our team is very flat hierarchy, so it's not a group where I tell everybody exactly what you have to do and the people just follow the orders. It's very much inspired by us discussing in a very interactive way and finding the way forward. So I couldn't even tell you, what exactly we're going to do in 5 or 6 years from now. It's really a path that we really discover together with the students, with the postdocs, and that we really require also the input from everybody working in the group. So it's a highly interactive process. And yeah, we have our weekly team meetings. We have our group retreats, which we have several nice places close to Munich where we go and have retreats with the group, where we spend the whole week and go there and discuss and invite guests. We have a lot of conferences going on here in Munich, also with our excellence cluster, quantum science technology, where there's actually a large community here in Munich working in this field. So yeah, but for me, that's basically how we do the interaction with the students and the teams. Did that answer the question?
Yeah, I think. Okay. Thank you so much.
Okay.
So maybe briefly for American students, there's a sort of like I don't know, people have said that like if you want to pursue an academic career in Germany or like Europe, it's better to get a PhD in the German system or in a European country. Do you think this is true, or like? And
no.
Yeah.
No, I don't think it's true. And I also don't think it's true that also a lot of people say if you want to pursue a scientific career in the US, you should do your postdoc in the US. And I think actually the people coming out of my group are a good example that this is not true. I mean, if you look, people like Monica Schleier-Smith at Stanford right now, she did a postdoc with me, with our group. There's Manuel Endres, who's now professor in Caltech, who was a PhD student, also postdoc in Munich later. Postdoc in Harvard. But so I honestly, I think these are just, I think in the end what matters is that you work on a good experiment in a good team. Everything else doesn't matter, honestly. And I think you have to choose whether you want to have this experience of going abroad into a different country and experiencing also the different lifestyle. And for German students, this is extremely appealing. So probably that many German PhD students, after their PhD, they go to the US to do their postdoc in the US. So that's very, very appealing for them to do that. And I hope maybe we can inspire you to also do the same thing and do your postdoc in Europe and come to visit us and spend your time here. And I think this is equally rewarding, and because it's not just about learning, in a different team, science, it's really also learning about a different lifestyle. And I think that's just as a young person is extremely interesting. was interesting to me also when I went to the US.
Maybe briefly as an editor's note, we'll have Monica Schleier-Smith in a couple of maybe months. But yeah, stay tuned for that.
Yeah, great. So you can ask her firsthand. So, but I think it really, there are so many examples now where show that really what only matters is that you really do good stuff, good research, and I think everything else is secondary. Okay, great. So yeah, let me get started then with the research that we're working on, and tell you a little bit. And what I basically, by training, I was never really so interested in condensed matter physics. I in Bonn University wasn't strong in condensed matter, and I was really interested in quantum physics. I did my diploma thesis on quantum optics on light matter interactions. And somehow it's strange that I ended up in quantum many-body systems. But I think, what really I learned to understand during the past years, that being able to do, quantum many-body physics in such clean environments that we have available now, and with these new microscopic tools that we have available now to look at these systems, the microscopic scale, this is a fantastic new tool. And I really enjoy working in this field and learning about all these fantastic condensed matter phenomena or quantum many-body phenomena in general. So this is our research topic, the fundamental interest in understanding quantum many-body system, how emergent behavior comes about, knowing the microscopic rules. We know everything is just Coulomb interaction. So the Hamiltonian is just Coulomb Hamiltonian. You write it down, it sounds like, what's the problem? Why can't we solve this? The problem lies in the complexity of these systems, that we cannot solve these complex many-body systems governed by just these very basic laws of nature, like Coulomb equation. And of course, this also has not only fundamental interest in science, but also there's now this whole application side to this in quantum science and technologies, where people really try to make use of this to develop new tools, such as new quantum sensors that harness those quantum features. And yeah, so basically you ask, why is it difficult to look at this many-body system? If you have a many-body system, you probably know that you have this exponentially large Hilbert space in quantum physics. So you have a very large state space of all possible configurations, exponentially large state space, and that makes it very hard to compute things. But really, this is not precisely true, because for ground states, typical ground states of a many-body system, this only occupies a very small part, and that's why there are very good numerical, classical algorithms that allow us to approximate these solutions. But there are cases where we indeed populate this entire Hilbert space, for example, especially when we look at dynamics in many-body systems, and then we really have to resort to new tools to explore these systems. And one system that is actually interesting in this context, also for its ground state properties, is the so-called Hubbard model. We talked about this already, the MOD systems that play a very, very important role in modern strongly correlated electronic systems. So, high TC superconductivity is believed to be contained in this very, very elementary Hamiltonian. And this is something we'd like to understand. And even after, 40 years of research on this Hamiltonian, we still don't know the phase diagram of this very, very simple Hamiltonian that I'll talk about a bit more, actually. What's also interesting, that this problem is a really nice current reference problem for modern quantum computers and simulators. We are in the era of quantum computing, quantum simulation. Everybody's excited about the possibilities, and you ask, what can you actually do with these systems? And you hear a lot of big claims. I don't want to maybe comment on all of them, but one of the claims you will also hear, that they can help us to solve problems in quantum chemistry or quantum materials. So in order to now judge if you have a good simulator or computer, it's good to have reference problems, and this strongly correlated electrons, strongly interacting electrons in the system are a very, very good reference problem that we can actually study with these systems. Okay, so what are the big questions we want to answer? So we know the microscopic rules, how, for example, electrons interact with each other. I said that's just Coulomb interaction. You learn that in your undergraduate course. But still, when it comes to predicting, material properties out of these very basic laws, when we have many of these electrons coming together, it's so hard to predict the material properties in many cases that we just cannot do it in classical computers, because the problem is so complex. Okay. And so that's the one question we want to answer. And then the second question we want to answer, how do I have to change the rules to, for example, get specific material problems? Yeah, so to have a designer material with specific tailored properties that I would like to basically have then in practice. And the claim then is that these quantum simulators and quantum computers can, in parentheses, as I said, in some cases help. And I think we should not overhype this. There are cases where they won't help, but there are cases where we think they can actually help to solve these problems. And we believe the progress in the future will be very exciting to work on these problems. So how does this quantum simulation approach work? So basically, the idea is we take the system we want to learn about, let's say this high TC superconductor, and then we talk to a person like Eugene Demler, who was also on your lecture series, and ask him, to write down for us a model Hamiltonian that he thinks describes the physics of this system. Okay, that's one thing we have to go do. And then he writes down this Hamiltonian. Doesn't matter now what this says, it doesn't really, it's not so important right now. And then this Hamiltonian, we try to implement in our system, in our artificial quantum system in the lab. And we let this system run. So we get a time evolution of this quantum state. And then we do a measurement on our apparatus. And then we get the outcome of what the system has evolved into. And we learn about the system. And by that, we try to close this feedback loop. And that's the spirit of quantum simulation. There's another way of doing this quantum simulation, and that is very close to the spirit of so-called adiabatic quantum computing, where you start out with a system in a very controlled initial state that you can initialize with high purity. So you can bring the quantum system in a very, very controlled initial state with an initial Hamiltonian. And then you very slowly change the parameters of this Hamiltonian so that the initial Hamiltonian goes to the final Hamiltonian. And then the adiabatic theorem will guarantee that if you do this change extremely slowly, then the ground state of this system will evolve into the ground state of this system. And this ground state of the final system might be something that's very difficult to compute or very difficult to write down even. So just by adiabatic evolution, by slow change of parameters, you evolve into this desired ground state of the final Hamiltonian, which encodes, for example, the solution to the problem that you're studying. That could be a physics problem, a chemistry problem, or as people are also interested in so-called optimization problems to encode it in that way. So if you think about it, what is then the difference? Well, quantum simulation is basically adiabatic quantum computing, but we typically do not have the control over all degrees of freedom that you would need to make a universal adiabatic quantum computer, but we can only do this for certain parameters in the system. So we basically are dealing with a restricted form of adiabatic quantum computing. So that's what a quantum simulator is essentially. It's a restricted adiabatic quantum computer.
So the adiabatic theorem breaks down for like where you have small gaps, and this makes a lot of like classical optimization or combinatorial optimization problems tough for quantum computers. How do you guarantee that this is not the case in this kind of framework?
Oh, this you absolutely do not guarantee. That's the big problem, actually. That's why a lot of optimization problems, I'm much more skeptical whether they will be efficiently solved by quantum computers, because precisely of what you are describing. Because the spin problems they map onto, so this final Hamiltonian that characterizes this optimization problem might have a structure with an exponentially small gap. And that means you need an exponentially long time to go through that system adiabatically so that you stay in the ground state. And that actually, for most Hamiltonians, especially these optimization Hamiltonians, they map onto crazy spin Hamiltonians where actually this gap is exponentially small. And I think for those class of systems, there's very little hope that we'll get any speed up through using a quantum computer or quantum simulator or adiabatic quantum computer and solving these problems. There is hope that you can find maybe some problems where this gap is not exponentially small, and people are just right now trying empirically. I think in general, we understand that for general class of problems, this is going to be always exponentially small. And I don't think that's why you're right. There will not be a lot of progress there, not a lot of hope, but people are just hoping that there will be problems which are more amenable, or which do not pose this exponentially small gap, which have a more finite size gap, but you can then ram through in a finite amount of time and find an efficient solution to the problem.
And you think finding like the ground state of some complicated many-body, or maybe not so complicated many-body Hamiltonian, is in the latter class of problems where the gap is not so small.
Yes, because the problems they map onto, exactly, those problems are physical Hamiltonians, and the physical Hamiltonians have a different characteristics that they very often do not have this closing gap. So for physical systems, we typically do not encounter this problem as much as we do for the Hamiltonians that come out of these optimization problems, which are really crazy type of Hamiltonians with non-local couplings, almost random, or very strange coupling strengths between spins that you model. So they're not very physical Hamiltonians. So these Hamiltonians are much harder than the physical ones. And maybe there's a deeper thing at hand here that, for physical systems, this is also why these systems are robust in nature, that this has to be like that. But that's just something I'm speculating maybe on. Yeah, absolutely. But that's my personal belief is that for physical systems, we'll have much better chance of doing this, this approach will work. For general optimization, I'm much less optimistic. Very, very, very good question. So you're a real expert. Very good.
This type of quantum simulation restricted to like Hermitian Hamiltonians, or like I know that adiabatic theorem breaks down for non-Hermitian systems. So are there any possibilities for using quantum simulation analogy?
Yeah, so right now everything we are doing is for emission systems. So, but you can also have non-closed systems where you, for example, pump the system from the outside or have dissipation, control dissipation, and that might open up completely different problems or degrees of freedom that can be interesting, but also detrimental. It depends a little bit. So people have looked at both questions actually. But what I want to focus on is mostly the emission part, where we just have a closed system and we just have emission Hamiltonians in the system. Okay, yeah, we're moving slowly, but let me just, but it's good. Yeah, it's great that you're asking questions. Please keep asking. If you compare this to digital quantum computing, the idea is basically very similar. In a digital quantum computer, you try to break down the time evolution of a many-body system into just a discrete set of gate operations. So you basically trotterize the Hamiltonian into very small time steps and try to build up out of elementary gates a very complex time evolution according to your model Hamiltonian that you want to simulate. The nice thing with the digital approach is that you basically only need a few elementary gate sets to build up this complex Hamiltonian. The downside is, of course, you might need huge amount of resources to do that. So the time steps you might need a lot of gates, you might need a lot of qubits to do an efficient representation of this model Hamiltonian. In the analog case, as I told you, we're just trying to implement directly this model Hamiltonian in the system and let it run. The great thing is, if we can implement it, we can run it very efficiently. The downside, of course, is if we cannot implement it, then we just cannot do it. There's no way for us to do that Hamiltonian. So we're not universal in a sense. We can just limit it to simulating what we can really implement directly in the system, but then we can run this directly. But if you look at modern, simulating and quantum computing platforms, you will actually find that there's no big difference between them. Actually, both approaches are pursued in both kinds of systems: atoms, ions, superconducting systems, quantum dots, photons. And I think it's really a bit depends on the problem and the spirit you're taking, which path you're going. And we are mostly in the quantum simulation part. We are trying to push the cold atom systems more also in the quantum computing part, and trying to build on some of the strengths we have for our cold atom systems. Okay, let me skip this part. And let me just mention one thing that's interesting when you simulate quantum dynamics of a many-body system. So you see this small thing here, that's a real material, okay? Let's imagine this is a real material. It's angstrom separations between it, and timescales are on the picosecond, femtosecond timescale for dynamics in this system. And remind yourself, what we are basically doing is building a microscope to build an artificial system that we can zoom into. So instead of just building a microscope to look into the system, we actually do the opposite. We just scale up the system by a factor of 10,000. So everything that's angstrom sizes in the real material becomes micron sizes in the artificial materials. And of course, you cannot do that in a real material. If you start pulling and on a real material, it will just break. So you obviously have to do this in artificial systems. But if you can do that, now everything that angstrom size is micron sized here. And that means now we're dealing with micrometer separations between these atoms. And we can now look at these atoms individually with optical means. It also means, remember, in quantum mechanics, if you go to larger system sizes, energy scales go down, right? And if you think of your square box potential in quantum mechanics, if you basically make it larger, the energy separations go down. And so everything that has become very fast in this real material has become very slow in this artificial material. So everything that's happening on the picosecond timescale and the real material on nano or femtosecond timescale is happening on basically millisecond timescales in these artificial systems. So that's also nice because we slow down the dynamics and we look at the real-time dynamics. We can now look at the real-time dynamics of these systems. Okay, here's a picture of now finally how we do this. That's actually a picture from Ted Hench in his labs, where he took a laser beam, expanded it through a telescope, and sent this laser beam through these 5 apertures. Okay, so this is just a cardboard with 5 holes. And then he just put a lens behind this cardboard and focused these beams down. And then, of course, you get interference from these 5 laser beams. And what you see out of this 5-fold pattern here in the cardboard here, you then get this beautiful interference pattern in real space, this quasi-crystalline interference pattern. So that's a real interference pattern. It's not a Mathematica plot or something. This is the thing you get out by interfering the light field. And it just shows you that we can create beautiful patterns of light by interfering light. We can create almost any crystallographic structure you want by interfering the light under the right angle in the system. And the light is experienced by our atoms as a very feeble, as a very weak potential. So through the so-called dipole force, these atoms that we can now put into this light fields really experience this as a very, very, very shallow potential. So we have to make the atoms very cold, but if they are very cold or cold enough, then they can be trapped in these crystals and move in these light crystal structures in free space in vacuum. And that's basically what we do. We can do this with up to a few thousand particles. We can do this with spin systems, so we can look at qubits. But as I said, we can also directly simulate bosons or fermions or mixtures of both and look at their motion in these crystals. So we really build artificial crystals out of light and study the behavior, the quantum mechanical behavior of the ultra cold atoms that we load into these systems. And by the way, if you want to know more about how this interference pattern has been taken, so here's Ted Hench's YouTube channel. So his username is superlaser123. And actually, I think there must be more subscribers by now because I keep advertising his YouTube channel in every single one of my talks. And but it's really great. It's a great YouTube channel. You have a lot of really beautiful optics experiments there. Also a very old experiment from Arthur Schorlow when he pops the Mickey Mouse in the balloon with one of the first lasers they were building at the time. So really I highly encourage you to go to the YouTube channel and have a look also. And you will see actually how this interference pattern was actually created. And you can have a look how he did that in his labs in Munich. All right, so we trap atoms in these light fields. And now we want to make them interact because interactions really make this really, that's the spice in the whole game. That's what makes this interesting. If they would just be non-interacting particles, it wouldn't be so much fun. It's really the interactions that make this interesting that allow us to do this in more modern condensed matter physics. So we have interactions that can come about through collisions, through dipolar interactions, or through Rydberg-van der Waals interactions when you excite an atom to a very highly excited atomic state, this Rydberg states. You can have so-called Rydberg dipole-dipole interactions, or you can place these atoms between 2 mirrors in a cavity, optical cavity, and the light bounces back and forth between those 2 mirrors. And every time it passes through one of the atoms and interacts with the atom and carries the information to the next atom and so forth. And like that, you can realize so-called all-to-all interactions where every atom interacts with every atom in the system through this light field bouncing back and forth between these mirrors. So that's how we typically realize interactions in the system. Another thing that's interesting to keep in mind, most of our experiments are completely isolated from the environment. So we do this in these ultra-high vacuum cells. Here's a picture of one of our experiments. Here's a coil that generates the magnetic field that levitates the atoms inside this ultra-high vacuum system. And we cool the atoms in these glass cells. And it's mind-boggling to me is just remind yourself you have these nanokelvin temperatures behind this glass cell where everything else is at room temperature, basically, on this picture. And it's not connected to reservoirs, so you can study the physics of isolated quantum systems, and that's interesting to study. For example, how does thermodynamics, how does statistical physics emerge in such isolated quantum systems? Because that's not a priori so clear. If you take a system, an isolated quantum system, and you shake it and move it about, how come that you can even use statistical physics to describe such a system so efficiently? Usually statistical physics and thermodynamics works well when you bring something in contact with another thermal reservoir, but here you're not bringing anything into contact with anything.
Professor, can I ask a quick question about this?
Yes.
I'm intrigued by the glass cell is already really interesting, but how are you generating your MOT? Are you using the norm or like the conventional heated oven technique, or like a cryogenic buffer gas beam or something like that?
Yeah, just in this case, it's just the normal MOT, but it's on a different chamber somewhere over here. And we use a magnetic transport to shovel the atoms from this magneto-optical trap region over here into this glass cell over here. So it's like a small magnetic levitation train. It's the same principle. So, we have a series of coils, and then we can make a small maglev train over a distance of 1 meter or 50 centimeters and move the atoms from the MOT into this region here, into this UHV glass cell region. So that's how we bring them there.
And are you generating the artificial crystal lattice in the MOT region?
No, the list crystal will be created here. So here, everything actually not all the optics has been removed, so you can get a good look at the glass cell. It will be completely covered. I'll show you in the next image actually how it looks in reality now in the lab. Yeah. So very good question, because this is how it looks in reality now. And if you've been to one of the experiments in one of these optics labs, this is how they typically look. Now there's the vacuum chamber somewhere over here. It's buried with tons of optics. You cannot even see that anymore. And all the laser systems are over here where we, generate all the light fields for the magneto-optical trap, for the optical lattices. So typically for the Rydberg laser excitation, so typically now we have 12 to 15 lasers that have to run simultaneously. And that's of course a huge challenge, to keep things running. And you need great students like yourselves to keep this running. Yeah. And you have to, if just one mirror is misaligned, then the whole thing is not going to work anymore. So you really have to know what's going on in these systems, have very deep knowledge. And of course, one current goal of our new experiments is to miniaturize this, to make this more stable, more robust, that this huge lab scale experiments eventually can be shrunken down to something much more compact and hopefully also more stable. But in the end of the day, these things are run off the computer. So we program them. We have our own programming system, and we program them to execute certain measurement sequences overnight, for example. And then the students come back in the morning and they read out the data and analyze the data, and then come back. We discuss it, and we discuss with the theory colleagues, and that's how the typical experiments proceed. So it's really a combination of all this optics alignment and setting everything up, and then running the measurements, checking the system, and then harvesting the data that you get from these experiments. I mean, we talked a lot about condensed matter experiments, but you can also actually do interesting experiments in other fields. So quantum many-body physics does not only mean condensed matter. It actually means also high energy physics. So one problem, for example, we looked at that was a lot of fun actually with Eugene, was the look at the Higgs mode, Higgs particle that exists in these ultra cold atoms or at these ultra low temperatures. So obviously we're not talking about the same Higgs particle like the one that the people at LHC make, but we're talking about a collective excitation mode of the many-body system that basically obeys the same equations of motion, the same relativistic equations of motion like a Higgs particle. Okay, so in terms of a quantum field theory, in terms of the dynamical behavior of this quasi-particle in our many-body system, it's like a real Higgs particle in the real system. Okay, but obviously it lives at, I think I calculated it once, 24 orders of magnitude different energy scales. But it just shows you the beauty of physics that, concepts that emerge at the ultra low energy scale suddenly find applications at the super high energy scale again. So it really shows how close these ideas are. So the problem we looked at, just to tell you, was, can such a Higgs particle exist in a two-dimensional system? And that question still today is not answered completely in analytical questions. So that's a very difficult analytical question. And we thought, well, let's have a look at it and try to help to settle the debate. And that's what we looked at. And we indeed found that this Higgs particle could exist in this two-dimensional world. There are also a lot of cool other things you can do. One other really nice experiment, I think that's fun to read up on if you're interested in learning more about our experiments, was this quantum matter at negative absolute temperature. So you might have heard about the concept of negative absolute temperature for spins. And what we did here, we built actually a full gas of atoms which move around in space, are not fixed in position, and showed what it means to have such a gas at negative absolute temperature. So a real gas at negative absolute temperatures. And what was interesting, that brought about the whole discussion, that triggered going back to whether negative temperatures truly exist, that brought us back to the foundations of statistical mechanics. And if you never had a chance, I really highly encourage you. There's this original treatise from Gibbs from 1902, I think, here on statistical mechanics. This is all pre-quantum mechanics, so they didn't know anything about quantum mechanics at the time, but a beautiful treatise on statistical physics, where he also discusses the different microcanonical ensembles that you could use, from which you could derive then different temperature concepts. So it's really brought us back to this pioneering, ideas of statistical mechanics. And well, just for me, fun, when I was giving a colloquium at Yale in 2019, I went, there's a graveyard in Yale in New Haven, if you can go and visit, a famous physicist buried there, but there's also the grave of Gibbs, and I went there and I put a stone on his grave, and that felt kind of good to connect at that moment. Yeah, so let me actually just show you a little bit of these beautiful ways of probing microscopically these many body systems and optical lattices, and using these tools of quantum gas microscopy. And the idea is basically the following, that if you have a many body state, in general, it's going to be in a superposition of different configurations of that system. And that's what makes this problem so difficult, because there can be an exponential number of configurations in the system, right? So that's why it's so hard to calculate this. But let's imagine we have something like that in our lab. Or let's say we have a material in a certain, many body state in our lab, and it's in this state system, this superposition of different configurations. And let's imagine you take a photo of this system where you can see each individual electron in that system with a single lattice site resolution. So what would happen to that system if you take a photo? If you had a camera that could take this, atom lattice resolved electron sensitive pictures. So what would happen is that this many body state would collapse onto one of the configurations in the system, and which one is completely random. You don't know which one it will collapse onto. Quantum mechanics only tells us the probabilities of which we're going to find different configurations. And let's say now in the experiment, we see this configuration, okay? And now the system is dead. And if you want to do another measurement, you first have to create psi again. You do another measurement, and the next time it maybe collapses onto another configuration. So it's a destructive measurement process. It has to be destructive by the principles of quantum mechanics. We cannot do anything. It's not an imperfection of the experiment. But each time it collapses onto one of those outcomes, we learn something about the system. And when we repeat this experiment thousands of times, we basically record probability distributions of different configurations. We in the end know how often did this configuration occur, that configuration, or this other configuration over here. And from these probability distributions, we can then calculate what the theoretical physicists like the correlation functions. Okay, so how do these systems behave? How likely is it, for example, to find an atom here, two atoms over here with a hole in between? Or how does a hole, for example, change the environment in the system of the other particles around this hole, around this dopant? So that's the questions we're interested in. And that's what we're really able to do with this microscopic technique. Yeah, so here's a picture of how this works. This is what was done here in Munich and in Harvard for the first time about 10 years ago, for the first time with these bosonic systems, where we create these optical lattices. We have a very good microscope objective to, observe the atoms. We shine resonant light onto them to make them fluoresce. So they just light up like small light bulbs. We collect the fluorescence from these atoms with the objective, and then we can see these atoms on our camera. And this is a picture of the fluorescence image of the atoms on the camera. And you can really see how each atom lights up beautifully with very strong signal to noise ratio, and we can beautifully see each individual atom in the system. We can also, then go in and not only observe atoms, but we can also send a laser beam in reverse into the system and move atoms around or control their spins with the same resolution. And this is just shown here just for fun. We made a psi out of 26 individual atoms, where these white spots, they are the lattice sites, the optical lattice sites, and we control the spins of the atoms to make this psi. As quantum physicists, of course, we like the psi out of 26 individual atoms in the system, just to show you that we can really also control individual atoms in this system. One thing we're working on a lot nowadays is to make much more flexible, optical potentials by using these digital mirror devices that allow us to, really project any arbitrary light pattern we want onto the atoms. So we can make this line, we can make exotic lattices, we can basically have two reservoirs connect with each other, we can have box potentials. See, these are all light potentials we can project onto the atoms. And these are then trapping potentials in which the atoms are trapped, in which we can observe them with these quantum gas microscopes. And here's just a picture to show you how this works. This is kind of the pattern we put on this digital mirror device. It's just an array of small micro mirrors that you can tip or tilt. This gives us this light field. We superimpose this on top of the optical lattice, and this allows us to structure the lattice into these double parallel rows that you can see here. We call these quantum ladders. So they are coupled one-dimensional systems. So there's one line coupled to another one-dimensional line. That's why it's called a ladder system. Yeah, and that's what you see here in this fluorescence image. We can go to pretty large systems nowadays. Yeah.
I have a quick question. How is I'm intrigued by this digital mirror device. So how is this different from something like a liquid crystal spatial light modulator?
You can also use a liquid crystal light modulator. That's also possible. That's typically used for phase control of the light field. Here we just have basically amplitude control, but both can be used. Both are used in the community, so you can use both options. Both are actually used.
Does DMB has an advantage of like faster switching? Is that a part of it?
Yeah, it does switch a bit faster, but it does have some problems also with ringing. So when you tell the mirror to tip, it rings a little bit, so it tips, but it keeps ringing a little bit. So it is a little bit faster than the liquid crystals, but typically on the millisecond range response times, whereas this can be in the fractions of millisecond response time. Maybe a factor of 10 better, but still I think not good enough to do really dynamics in the system. But you can change patterns from one pattern to the next. If you turn it off and turn it on again, that typically works quite well in the experiment. Absolutely. Yeah, just to show you, we can go to pretty large system sizes also now. So this is some of the largest system sizes we reached recently with about 2,500 atoms in this so-called mod insulating state, where you have exactly one atom per lattice site. And actually what you see better here are the defects of this mod insulator. So each time there's a black spot, there's actually a single atom missing at that site. Okay, so this is a very homogeneous filling, exactly one atom per lattice site. And whenever there's a black spot, there's basically a thermal defect there, which by temperature creates a defect and removes an atom there. And if we cool the system a bit more, we can reach very homogeneous fillings for these systems where you have, I don't know, 99% filling fraction of the lattice sites with exactly one atom. All right, I see I'm moving too slow, so I should just maybe show you one cool thing of how to detect these. One other technique I want to show you how to observe these atoms, which is pretty cool, that we developed last year. Is so far I showed you how to see atoms, but you don't really know what spin state the atoms are in. So you are not doing a spin sensitive measurement. You're doing a density resolved measurement where you see, is there an atom or is there no atom? But what we'd also like to know when we work with spin mixtures is we'd really like to know, is there a spin up atom or a spin down atom there? Is there a doubly occupied site? There's an empty site. So that's what we call full spin and charge resolution. And to do that, we developed a technique, which I'd like to just show you briefly and show you a picture how this works. So let's imagine we have a configuration like this in our system, and we want to see that. And what we do then is we basically split the system into two layers, one which only has the spin up atoms in them, and the other one which only has the spin down atoms in them. So in a sense, what we do is a Stern-Gerlach separation. We do a very controlled Stern-Gerlach experiment where the spin ups with their magnetic moment positive move in the upper plane, and the spin downs with a negative magnetic moment move into the lower plane. Okay, and once they're separated like that, then we can really take two photos, first by focusing our objective onto the lower plane after separating it. Then we know where the spin downs are. Then we focus the system onto the upper plane. Then we know where the spin ups are in the system. And then we put this information together and we basically get the whole information of the system. So let me show you this. So you have this monolayer, which is what they want to image. You split it through this Stern-Gerlach separation. You increase the separation between the two planes, so you can really nicely focus on the two planes separately. And then you make first an image of this plane, gives you this image, make a photo of this plane, gives you this image. You reconstruct where the atoms are on the lattice, and then you put the two together, and then you get the full information of where the spin ups and downs are and where the doubly occupied sites are, where the holes are in the system. And this is now super valuable information because now you really know everything about the system. You really know where the spin ups, downs are, holes are. And this is something that we really wanted to investigate, is how do, what is the crucial question in these Hubbard systems is, how do these charge impurities, how do mobile holes, for example, change the magnetic properties of the system? So that's a very fundamental question in the system, something we looked at in 2019. And it's conceptually a simple question. You're just asking the question, how does a single hole, a single movable hole here, change the magnetic environment of such, for example, an antiferromagnetic system where you have spin ups and downs in the system? And this is a difficult question. It was looked at by, three of the greatest theoretical physicists of our time, Charlie Kane, Patrick Lee, and Nick Reed, worked on this in 1989 already on this Gedanken experiment of a single hole in this quantum antiferromagnet. And yeah, so this is indeed, let me just skip the physics. Let me just show you that we really can now take photos of this object. Okay, so we can really take photos where we look at these dopants. In this case, actually, we made use of not a hole, but a doubly occupied site, which can move around in the system. And we looked how the magnetic correlations, the spin-spin correlations between different sites. So these are these ellipses here, which encode the spin-spin correlations between these different sites, the atoms on these sites. So the color tells you what kind of spin-spin correlator you get there, how these are distorted when you have a mobile impurity here in the system. And if you go, for example, look at these diagonal correlators, you actually see that they can even reverse sign compared to what you have in the background of the system. So for the first time, we can really take microscopic pictures how these atomic impurities distort the magnetic environment in the system and learn something about this. And one of the hopes we have is that by studying such systems, we can basically, understand the mechanism of binding, for example, of holes. When we have two holes, two impurities in the system, how they bind together to form something like pairs that can then condense, that can give rise to high TC superconductivity. That's basically the long-term goal, the prospect of why we're doing this, why we hope this is an interesting route to explore. Okay, so just to put this in context, where are things heading up next?
So maybe I'll just interrupt very quickly as a moderator. So this might be a little unprofessional, but we have no time constraints, so it's all up to you. Like, you don't have to rush. Like, anything you want to present, go for it. Like, it's
okay. It's okay. I'm wrapping up, and I think
don't worry. You don't have to wrap up. Is all
okay.
I'm saying.
Okay. So where is the field, heading? And let me compare a bit to the different technologies we have out there on the AMO side of things. So you have these fantastic experiments on ion traps with, really pristine level of control, up to 50 ions in the system. We are seeing these beautiful tweezer experiments where you have also tried to bring this control level now to larger systems with Rydberg interactions. And then we have the lattice systems, which can be even larger. And we hope we can scale them up with these optical cavities to a few tens of thousands of atom systems. And so I think we're trying to, bring this level of controllability up here, while the ion traps are trying to scale up, keep their controllability and scale things up. And so I think it's all these platforms are trying to come together, and we're trying to make use of the best of the techniques that we have in these different platforms and bring the advantages of each of those platforms together to each other. One, I think, big advantage we have compared to solid state systems is that all atoms are the same. By nature, they're built the same way, so we don't have to deal with any inhomogeneities, imperfections in our construction of the qubit. They're just the same by definition. So that's, of course, a huge advantage. We have to put a lot of work. I mean, what I swept under the rug a little bit when I said, we use these micro devices, digital mirror devices to make these nice potentials. If you look carefully, you look at this potential, it doesn't look so great. I mean, there's some roughness here. The light pattern isn't entirely smooth. It would be much nicer for a box potential if this were really super smooth. And what we have to fight against is laser speckle. You know this very well, that with high power of a laser, that's nice. You also get a very detrimental thing, which is coherence. In this case, it's detrimental. For other applications, of course, nice. And this coherence of the laser light gives rise to, that everything you scatter off creates interference, and this gives rise to this laser speckle. And we have to really think about developing new light sources we're working on, for example, very intensely in Munich, that give us high power, but at the same time remove this speckle effect, so that are broadband incoherent, but still have this high power and don't heat the atoms. So there's a lot of technical developments we have to think about. But if we can do this, and we're very close to doing this, then I think it's, we have huge potential, because then you can really use these digital mirror devices to program these systems at the microscopic scale, at the scale of tuning the potentials or barriers between individual lattice sites, and having the ultimate control of over these lattice systems that we can project onto our atoms with a quality which is as good as my LCD screen is showing you on your screen, or your projector in a lecture room would project onto the lecture screen. Yeah, in terms of physics, what kind of physics do we like to explore? I told you a lot about the condensed matter physics applications. There's a lot of physics that are going on in the direction of non-equilibrium dynamics, trying to understand how does statistical physics, thermodynamics come about in isolated quantum systems. When are conditions where this breaks, when we cannot rely on the fundamental principles of statistical physics. But we also look at, as I told you, interesting phenomena from high energy physics. Cosmology is interesting, and there are a lot of applications going in the direction also of trying to build new clocks with these systems, new atomic clocks, which can serve for better navigation purposes, or trying to build just, from a quantum optics perspective, these arrays are great because they can also serve as novel quantum light matter interfaces. So I really hope that in the next years, we can use these fantastic, potential to image these systems at a microscopic scale, together with the potential to realize very, very interesting states of matter, to discover also new states of matter. So to push physics into a regime where we don't know the answer, we cannot do the calculations, and we're really just in an exciting regime of discovering entirely new physics phenomena. And that's, of course, for an experimental physicist, that's the biggest thing you can do. You can just discover something completely new. Yeah, let me just finish by just showing you that this work, of course, not done by myself, and we have a great team of people working on these experiments. And some I want to highlight is Christian, who was a team leader, who's now in Tübingen. Timon has taken over. Jaya and Yanis were the senior PhD students on the experiments. They now left. They're been taken over by Dominic and Sarah, and Mim and Guillaume were the postdocs on the experiments. And as you already saw on my experiments, we really have very, very close contacts to theory. We had a lot of collaborations with Eugene Demler's group, Fabian Grust also involved. So very, very close connection to theory is always a very intimate exchange in our field. And that's a lot of fun because for me, you know, I always learn something new when working with them. This is the rubidium team on the rubidium gas, quantum gas microscope. So you see it's also a very international team coming from all different places in the world. And yeah, so what can I say? If you want to join us, also if you want to, I can just highly encourage you to come write to me if you want to join one of our teams. Munich, I think, is a scientifically very good place to be in terms for quantum sciences in general. It's also a beautiful place to be. The Alps are very close to us, so we have Great Lakes. The Alps are close by. It's a very nice city to live in. So it has a lot of living quality. And if you really would like to do that, we have a couple of new projects that we're starting right now with actually a great team of people that are listed there. And if you would like to join one of our teams, I just encourage you to go to our website or just write me, drop me a note, drop me an email, and we can see if we can find something exciting for you as well. All right, I think that's it. Ran a bit over time, sorry for that. But
no, please, yeah. This is absolutely wonderful. So if you have time, we might open for some questions and keep it a little abbreviated. Does that sound okay?
Sure. Go ahead. I'm still doing fine.
Cool. All right. So yeah, do people have questions?
Or maybe to start off, I have one more question that I've been thinking about since well, I recall the slide that you had of the monolayer, and then you basically applied you introduced, I presume, some sort of magnetic field or other perturbation to split the monolayer into a bilayer with some sort of spin up and spin down states. A lot of people are some people are working on like optical lattices with, say, like molecules now, or trying to assemble like optical lattices with molecules, things like CAF and that sort of thing. Well, do you see, and like there are a few like advantages to that, like the longer coherence time for molecules, and it introduces like interesting like long range interactions because of the larger dipole moment of the molecules. Could you do like some sort of similar experiment? Are there other applications with optical lattices that you could apply in this kind of like a system where you're basically doing the monolayer splitting and then recombining them to find to identify the holes and the overlaps between the two?
Yeah, we didn't think about in this context, but for sure the same principle should work in one way or on the other there as well. One just has to think out the sequence in detail. We are working on putting polar molecules, in our case sodium potassium, in these optical lattices and studying the dipolar physics of these molecules in the lattice. And as you say, that the dipolar interactions are what makes these interesting, that you have the long range dipolar interactions. So that's another route. I didn't focus on that. That's a very strong activity also in our group, where we have very encouraging results recently from sodium potassium, bringing that into the quantum degenerate regime. And then of course, eventually we want to implement also the same techniques that you see here in that system. But we're so far still in the state where we have to generate these degenerate systems first. But we already have in mind that we want to do high resolution imaging, maybe not single molecule site resolved imaging, but high resolution imaging. And keep in mind, with the molecules, you have to bring them close to each other. If you don't, I mean, even for the bioalkalis, the dipole moment isn't so strong. So if you cannot go to these large separations like tweezer traps, then the interaction strength will already be not so large. So having them at lattice spacings with 0.5 micron, for example, is hugely advantageous, Because remember, the dipole interaction scale is like 1/r², right? So that gives you a big booster in terms of interaction energy.
Or the potassium sodium, was it the molecule that you're working on? How are you doing cold dissociation for that, or are you like slowing, or are you generating the molecule in some vacuum chamber and then slowing it afterwards?
No, we're just doing the standard way of creating a double degenerate gas of sodium and potassium, and then doing Feshbach association and stir up to the ground state. What we had to learn in this system, which I think is new, and that's what's exciting, that we had to find a pathway to circumvent the otherwise strong losses in the system that prevent you to get very, very degenerate. But we now have very encouraging results that we hope will publish soon, that we can really get deeply quantum degenerate with these molecules. We've found a pathway to circumvent these losses, so we can make deeply degenerate sodium potassium molecules. So that's very exciting. And of course, the next step would be to see the exciting manybody physics with these dipolar molecules.
Yeah, very interesting. I look forward to that publication.
Yeah.
So stepping back a little bit, maybe. Sorry, before maybe I ask, other people who would like to have a go. Any?
Just a quick question on how to measure the correlation functions. So you take multiple shots of a quantum system, and then you. So I guess the first question is: are you just taking a subsystem, like a smaller part of the huge system? And would you need exponentially many shots because you have this exponentially many degenerate states?
Yeah.
And,
yeah, very good question. Yeah. So first of all, we are not looking at a sub. We make a photo of the entire system. And now the question of how many shots you need to get your correlation function to a desired accuracy depends on the size of your correlator. So if it's a multi-point correlation function, this might require many more shots. And if you want to basically have a correlation function over the entire system, this might require exponentially large number of shots also. So then you have a problem again. But typically you're not interested in that. So the thing is, in these physics problems, you're interested in let's say 2-point correlations, 3-point, 4-point correlation functions. 2-point is something standard for even material scientists, but already 3-point, that's something they cannot measure. So this is something where we can really add something new. And 3-point is still not such a large correlation function that you require a huge amount of shots. You can, still can require a few thousands of 10,000s of shots, but it's not exponentially large number. So this will grow with the correlation function you're measuring. The more higher the correlation function you're measuring, the more number of shots you will need in your experiments to get that down to, let's say, 1% precision level.
So is this like, if you want an O of 1 like correlator, you need n to the, or like some k correlator, you need n to the k shots or something like this?
Yeah, I think this depends a bit on the correlator and the details, but I think roughly that's right.
Yeah, thank you. It's very remarkable that you can measure like the off-diagonal correlator in the
yeah.
Thank you.
I had a few questions, so if other people want to ask, please go ahead. But if not, I'll ask 2 sets of questions. So one question is about a slide that you kind of, I think, skipped over, but you have a Fermi-Hubbard phase diagram that you guys are exploring. And for me, these experiments are super, super cool. But like one kind of question is whether you can access, like temperature regimes that in which you can see like the kind of superconducting dome, et cetera. Is like, I've heard that this is a limitation, or like, yeah. And maybe the second question is like, do you expect that you'll be able to see like the kind of superconducting physics in like the high TC superconducting physics of these superconductors? I guess is a bit of a loaded question. Yeah, maybe I'll ask that first and then I'll follow up.
Yeah. So I guess there are 2 answers to this question. One, we have to say we don't even know whether in the Hubbard model there is this dome. Okay, this is the phase diagram of a real material where we have this D-wave superconducting dome. So let me just explain what this phase diagram shows to everybody. So here's the temperature scale. Here's the doping of the electronic system. So how many holes you put into the system. So if you have no holes in the system, you see you have this phase, which is called the AF phase, which means that the spins align antiferromagnetically. You have a so-called Heisenberg antiferromagnet. So the spins, you have no holes, you have just 50% spin ups, 50% spin downs, and they will just align in a checkerboard pattern. Simple picture. And then we see if you introduce these holes, and this is the experimentally measured phase diagram, you get this dome, what people talk about, where for a certain range of dopings at low enough temperatures, you get this D-wave superconducting phase, ITC phase. Now there's the conjecture that the simplest model, the simple Fermi-Hubbard model of just spin ups and downs in the lattice with on-site interactions gives rise to this physics. I think a lot of physicists believe that, but it's not even clear. So we don't even know whether that phase exists. So the question how low we have to go in temperature, we really don't exactly know, because we don't even know whether that phase exists for us. But what I want to say is there's really a lot of exciting physics. You don't have to go down to this energy scale to see physics that's relevant to understand this energy scale, because a lot of the relevant physics also happens at these more elevated temperatures, where you see these things that's called this pseudo gap phase, strange metal phase, some different weird orderings here, charge orderings. So that's all happening at higher energy scales. So I think by trying to understand this problem, we can already learn a lot, even being at these higher energy scales. But of course, still, you're absolutely right. We want to push temperature as low as we can in the system. And so we have to devise new cooling techniques or new techniques how to push that temperature down. I think right now we are close to observing pairing effects between holes, so that we can really see that there are pairs forming between two dopants in the system. And the next step would be then to push temperatures maybe so far down that you could see, for example, if you know this stripe ordering, there are certain kind of density patterns that form in real superconductors that you could see that in these systems. That would be a huge success. Mm-hmm. And I also should say that, you know, now the experiments, if they can push a little bit lower in temperature, it will be out of reach for classical simulation techniques. Mm-hmm. So it's already at the limit, pretty much at the limit of what you can do with classical simulations.
Okay, so this leads to perhaps a second question, which is, I think, a little less coherent, but hopefully we'll be able to assemble something. But so in a typical quantum computer, like kind of piggybacking off of what you said at the end, like a typical quantum computer, the regimes that are kind of inaccessible to classical computation are kind of on like modern devices are set by decoherence, right? What is the equivalent, I guess, to decoherence in your system that is what inhibits you to lower temperatures? Is it just the lowering of temperature, and how should we think about this?
It's finite temperature, it's fluctuations of the lattice potential. You know, there's just technical noise in the system as well. You know, how stable are these potentials? Actually, they're shaking a little bit. They're shaking in amplitude, they're shaking sideways a little bit. And this is, of course, all there's magnetic field noise in our system. So that's, of course, all contributing to decoherence effects. Mm-hmm. So this is, of course, something we work on a lot to keep these technical influences as much out of the system as we can. And I think
maybe I'll phrase, I think so I understand what you're saying there. I'll phrase the question a little bit different. So like at the moment, the circuit depths that you can go to on like real quantum computers are super limited, right? When I look at this phase diagram, you make a statement that like some parts of this are classically accessible and some parts of this phase diagram are classically kind of intractable. So what is the kind of equivalent measure for circuit depth for your quantum simulator, if we're kind of borrowing language from the quantum theory?
Yeah, okay, so let me go back to this slide. It comes back to our original slide where we compare analog quantum simulation to digital. So this is basically gives a little bit insight. This is a dynamics problem we've been looking at, and this was together with Matthias Troja from Microsoft, Andrew Daly, and Peter Zoller. And it was try to answer maybe this question that you're asking. You know, is it better? How does a digital quantum computer perform relative to an analog computer that we have today, analog quantum simulator? So how good would the digital quantum computer have to be to do what we can do on the analog system for the specific problem that we can implement? Mm-hmm. Okay, that's what we also have. That's the catch we have to say. So for the specific problem that we can implement on, let's say, these Hubbard models, that we explained, and we look at some dynamical evolution, we can look at, for example, 10 by 10 systems. That's fairly typical, 100 atoms. We have maybe some errors in calibration. We have some decoherence effects that we can take into account that we know. And then we can calculate the time evolution of this, how far we can get with this system. And then we can ask, how good would a digital quantum computer have to be to perform the same calculation? Okay.
Yeah, okay, I see.
And this is what these numbers show you here. To map the same fermionic problem onto a digital-based quantum computer, you would need about 1 million gate operations, and the fidelity to each of those gate operations would have to be this number to achieve that. Okay, and that's far away from what people have accessible today. Maybe not in the future, but right now, I think this just underlines what I wanted to explain in the beginning. You know, analog quantum simulations right now in this system, in this era of NISQ, these noisy intermediate scale quantum systems, are advantageous for studying the dynamics or ground state problems if you can implement the problem in this analog way. You are superior compared to the digital system. Of course, the digital system promises once error correction is there, then it will of course be at an advantage. Then this will be turned on its head. But to be there, you have also a huge overhead. And yeah, so this is what we try to estimate here.
Well, okay, yeah, that's kind of perfect. Okay.
I guess yeah.
The other thing that like maybe, do you want to talk about the Fermi quantum processor stuff, or it's fine if you don't?
Sure, I can tell. Well, we have this new project where we basically want to combine, I don't have any slides on that, but where we basically want to combine the advantages of this, you know, with this lattice approach where we can detect individual atoms on the lattice sites. Sorry. We basically have this analog operation mode where we can study these fermions on the lattice, where we can combine this with the tweezer approach that I talked about before, where we can move around, for example, atoms in these lattice sites with optical tweezers, with focused laser beams. We can pick up an atom here, move it over here. And then by using the so-called super lattice techniques, where you can bring two of those sites into contact with each other, you can, for example, merge two of those sites, have these atoms undergo a controlled collisional interaction, then separate them from each other. We believe we can have, you know, very, very efficient gates, digital quantum gates with very high fidelities in these systems. And that's something we want to try to combine. So we want to build on this expertise on using these optical lattice systems, want to bring in the optical tweezers, want to bring in this new mode of digital gate operations in these fermionic systems, but still also retain the advantages of this quantum simulation approach to build basically a next generation system for quantum simulations and quantum computations based on these fermionic type of qubits. And so yeah, that project is just starting. So we're looking for interested people who want to sign up for that. And I think it's going to be fun because it really builds on, you know, bringing the strengths of those different platforms, the tweezer platform and the lattice platform together, I think for the first time.
Awesome.
Great. Sounds wonderful.
Thank you. Yeah, thank you so much, Professor. Cool. Oh, sorry, is there? Okay. Well, wonderful. I wanted to thank you again.
You want to say something? Or?
Well, I just have one more thing actually. When you on one of the slides, and when it comes to negative absolute temperature, what do you mean by that? Like, what do you mean by negative? When you're going through the slides, I couldn't understand it.
Yeah, so really, yeah, what it means by negative absolute temperature? Well, it would be a gas where basically, you know, the occupation of the many-body states is inverted in that gas. And so you basically you usually, you know, remember, if you have in normal positive temperature, you have exponentially decaying population of your many-body states, the Boltzmann factor, e to the minus e divided by kBt. Okay, so you have an exponentially decaying population for your many-body states, where E is the energy of your many-body states. So that's for positive temperature, okay? So for negative temperature, you actually have an inverted distribution, where you grow, the occupation increases exponentially with the energy of the many-body state. If T goes to minus T, and just write down your Boltzmann factor, e to the minus E divided by kBt, and take T to minus T. So you get your exponentially increasing population. Now that can only work because your probability distribution has to be normalizable, right? That can only work if you have an upper bound in energy in the system. So you have to prepare in the lab a system which has an upper bound in energy. And if you can prepare this upper bound in energy, then you can have you can realize negative temperatures in this gas. And this gas has crazy properties. Just to give you things, for example, you can realize a Carnot engine which has larger than 1 efficiency, something they told you cannot exist in normal Carnot engines. It's also a gas which has anti-friction. So if you shoot an impurity through that gas, that impurity will not slow down, it will actually accelerate. And it's actually also a gas which has negative absolute pressure. So it's a gas, usually, when you want to compress a gas at positive absolute temperature, you have to perform work on the gas to compress it. This is a gas actually where you have to basically exercise work on the system to expand it. So it has really some crazy properties, this absolute negative temperature gas. And that's what we realized in the system.
Oh, that's cool. Okay,
Yeah.
And one more thing, actually, you said if you're interested to join, so what if I looked into the QR code onto the last slide, and all it says I have to submit an email to you. Is that the case?
Yeah, that's right. There's no mode.
Right.
Just send me an email with your application that you're interested, and we'll provide you with any further information. Yeah, that's great.
That sounds cool.
Please come in. And I should say one thing that US students don't know: if you come as a graduate student to Germany, it's free, right? There's no student fees, no fees you have to pay. So I think there's only 100 euro or so, or 200 euro for your semester ticket, which buys you even a public transport ticket for whole of Munich. So I just want to advertise it's also quite economical.
I was wondering about that too.
And we encourage, there's no for foreign students and no fees in Germany. So if you come as a foreign student to university in Germany, you want to study there do your PhD or your master study or master degree, no fees.
Professor, I had
of course, that shouldn't be your prime reason to come. You should come because it's a great place. But I think it combines both things.
I mean, this is a very interesting subject, especially with the applications with the.
Yeah, I'm glad I got you excited. That's great. So get in touch and can see if you're interested in coming. We also have, summer internship programs if you want to maybe just come 2 or 3 months. We also had a lot of exchange programs with MIT program. There's this MITSI program at MIT where we had a lot of international exchange students visiting us for a few months. And, actually a lot of people in Harvard who are now at Harvard spent some time with us one time or the other. So if you want to do that, just get in touch with me. We can see if we can find a suitable program for you if you want to start out spending a few months and see how it is and working with us. And maybe you find it's so exciting that you want to stay a bit longer.
Yeah, Professor, I just had maybe one more question before we close. And thank you also for staying so far over time. Really appreciate it. If there's time for one more question. You had a slide about your comparisons between the quantum simulator and the outlook for the quantum simulators and the quantum computers. And this, in particular, I think the last row was about the scalability. And I think there was a mention about basically
this one.
This one.
This one, yeah.
The scalability in the near term. I'm intrigued that you mentioned that there's a direct path to like 10 to the 3 or 10 to the 4 particles in the quantum simulator system, maybe similar to the lattice system you were discussing later.
Yes.
I'm interested in how you propose or what this direct path is, because from my limited purview, it seems to me that there is like a lot of the similar problems that one encounters in like a scalable quantum computing system with the quantum simulator system, what with the low coherence time and pretty like relatively low tolerance So what is this like kind of direct path to like a really scalable system?
Well, scalable for quantum simulation, I would say that's a different thing from scalable for quantum computing, for fault-tolerant quantum computing. So again, because I think what we want to measure in these quantum simulators is maybe not that, let me put it in the right way, not as challenging as what you might be trying to do in an error-correcting quantum computer. Of course, that's simpler by itself, but you still have to get the system to scale up to these system sizes. I mean, right now I showed you pictures of these, few thousand, 2,000 particles we can already do in the lab today. We've seen in the Rydberg tweezer arrays, we're seeing now 200, 300 particle systems. I think we're going to see very soon with these cavity techniques to enlarge, enhance the powers, the optical powers to create larger scale lattices. We're going to, right now, we're just basically power limited. If you ask me how large of a lattice can you make, we're mostly limited by the laser power we have available to create deep enough optical lattices that we can use for quantum simulation. So these optical cavities that let me go to this slide in the end, actually show you this. Let's go forward again. Come on here. Sorry, it takes a bit. I don't know if you remember this cavity picture. This is our path forward to making these systems large. And again, solving the temperature problem is another question, how to get to lower temperatures. But one really technical problem here's the picture. One real technical problem for us is really getting enough power. You want to make the laser big, right? If you want to make the laser big to create large optical lattices, you're going to have low intensity because your diameter of your laser beam is bigger and you just have limited amount of power, even with a 50 watt or 100 watt laser system that you can buy. And that's not good enough. So what we are using is these monolithic cavities. So this is a block of ULE glass where we've bonded these mirrors onto these glass block. And it's all self-aligned. You don't have to align anything. It's monolithically contacted. And when we send light in there, we get power enhancement in the cavities, and we can get very, very large wastes here, very large diameters of the laser beams that circulate in this optical resonator. So we hope we can make very large optical lattices with tens of thousands of lattice site, given the available light power that we can send in from the outside.
Okay, yeah, I see. And so in that lab picture, I know, so the duplicity of your lasers is just a power issue, right? It's not, you're not trying to like address any additional states or whatever. And any okay, I see. Interesting.
Yeah. Right here, it's just a simple power issue. How can we make large lattices, large number of lattice sites, given the available power that we have?
Okay, awesome. Yeah. Okay. Thank you so much. And